Good evening, everyone. I hope you have understood the introduction of discrete Fourier transform that we have discussed so far, and the properties of dual factor. You remember dual factor? I've discussed it in my previous lecture. It's just a trigonometric constant, which is having two properties basically: the periodicity property and the symmetry property. Yeah. Now, in this lecture, I'll be discussing regarding a very important concept rather than you can say. It's called zero padding. Now, in discrete Fourier transform, or rather than in short, you can say DFT, what is zero padding? Do you know? Anyone? Any idea? Zero padding is nothing. It's a very simple concept. It is nothing but add zeros. Where to add zeros? Add zeros to the end of a signal. Now I will be asking, what kind of signal? To the end of a signal means to the end of a time domain signal. Clear? Why? Why will we add zeros to the end of a time domain signal? Just because to increase the length of the time domain signal. Clear to you? So I'm again repeating. Zero padding is simply referring to add zeros to the end of a time domain signal to increase the length of it. Okay. Now, what is its use? Do you know? Zero padding in the time domain is used in practice to compute heavily interpolated spectra by taking the DFT of the zero padded signal. Clear? Now, in digital signal processing, we are using this zero padding concept. I'm telling you, in digital image processing also, this padding concept is used. Here, this padding concept is used not only in DSP, digital signal processing, but it is also used in DIP, digital image processing. Now, to all of you, I'm sharing my screen over here, and you'll be getting to see the notes of my zero padding. Okay. So you see what's written here. Zero padding. What I've written. Now, in mathematical terms, let us consider xn having length L such that xn equal to x of 0, x of 1, x of 2, x of 3, rather than you can say dot dot up to x of L minus 1. Where, what are all these? These are L number of samples. Remember samples? L number of samples we are saying, we are considering in a signal xn. Now, here, minimum number of equally spaced frequency points that can be calculated between 0 and 2 pi without time domain aliasing is L, capital L. I repeat, here, the minimum number of equally spaced frequency points that can be calculated between 0 and 2 pi without time domain aliasing is L. So what do you mean by time domain aliasing? It's a new term for you, aliasing. We call aliasing effect. So what is it? In signal processing, aliasing basically it's an effect. I've told you. It's an effect. What does it cause? It causes different signals to become indistinguishable when sampled. Indistinguishable. Now, if I can't distinguish you from another fellow, means to me all are equal. If I can distinguish, then I can designate you as a different person and him as a different person. The same thing is indistinguishable for aliasing effect. So what did I say? In signal processing, aliasing is an effect that causes different signals to become indistinguishable when sampled. So aliasing can occur in signals sampled in time and in digital signal processing, aliasing is greatly necessary. So here the frequency resolution is 2 pi by L. Okay. Before we have seen already it's 2 pi by N for N samples. Now for L samples it will be 2 pi by L. Very simple. Now you see the frequency resolution. This frequency resolution, what is the frequency resolution here? It's 2 pi by L. So this frequency resolution will be poor if the straight line interpolation of frequency samples are indicated by DTFT. Now what does this mean, DTFT? This DTFT means discrete time Fourier transform. It is possible to obtain a better representation of magnitude and phase response if we increase the number of points between 0 and 2 pi. So increasing the number of points between 0 and 2 pi will give us a better magnitude and phase response. Clear? So this can be done. How will we increase the points? We can't increase any arbitrary points, isn't it? So we simply increase the number of zeros. We simply insert zeros in the sequence such that xn equal to, now the sequence becomes xn equal to, the starting everything is same up to L minus 1. You can see x0, x1, dot dot up to x of L minus 1. And after x of L minus 1, we increase the length of the sequence by adding many zeros to it. Clear? So this method of improving the frequency resolution is called zero padding. So to have n frequency points between 0 and 2 pi, we'll have to add how many zeros to the sequence? Obviously n minus L number of zeros to the sequence. So the new sequence has length n and its frequency resolution will be 2 pi by n. Clear? Now this is all about zero padding. It's an important concept in DFT. There is no numerical related to it basically. It's a concept. Now we'll see discrete Fourier transform as a linear transformation. Now what do you mean by linear transformation? What is linear transformation? You see, linear transformation means we are having two formulas. One for DFT and one for Idft. What is this DFT and Idft? DFT is our discrete Fourier transform. Idft is our inverse discrete Fourier transform. Clear? Now, for DFT, x of k, as the formula says, is x of k is equal to summation n equal to 0 to n minus 1 xn into Twiddle factor to the power k into small n. For Idft, x of n means the normal sequence. Again, it's achieved by 1 by n summation k equal to 0 to n minus 1 x of k into Twiddle factor to the power minus k. Clear? So where Wn, the Twiddle factor, is given by e to the power minus j 2 pi by capital N. What is capital N? Remember, in my last lecture I have told capital N is the number of samples. Clear? Now, you can find the n point DFT by a total of n square complex multiplications and n into n minus 1 complex additions. Okay, you can find n point DFT as n square complex multiplications and n into n minus 1 complex additions. Okay, now we can view, we can view the DFT and Idft as linear transformations on sequences xn and xk. This is a linear transformation on xn, and this expression shows a linear transformation on xk. Remember, your input is our xn, our output is xk. Your input is xk and the output is xn. That's why I've said, so from DFT shows a linear transformation of xn, and IDFT shows a linear transformation of xk. Now, one can express xn, capital Xn and Wn in matrix form. So now we will represent in matrix form. Now what is xn, small xn? Small xn is nothing but the endpoint vector of signal response. Endpoint vector of signal response. Capital Xn is the endpoint vector of frequency samples. This is the endpoint vector of frequency samples. And Wn, obviously it's a n cross n matrix, isn't it? Now you see, let me go to the next page. See, xn, my normal signal is x0, x1 up to x of n minus 1. My sampled signal, x0, x1 up to x of n minus 1. And what about my doodle factor matrix, Wn? Wn, the first row and the first column, all are 1. Now from the second element of the second column, you see the power of Wn is increasing, 1, then 2, then up to n minus 1. Here it is Wn to the power 1, here it is Wn to the power 2, up to Wn to the power n minus 1. In the third column, though as usual the first element is 1. In the second element, Wn to the power 2, then 4, then 2 into n minus 1. Means it's a just, what is it? What is the difference within this column and this column? Between this column and this column, I have multiplied the power 2 with each term of this column, and I have got this column, isn't it? So likewise, you go ahead, and the last column, the first element will be 1 as usual, and here it will be Wn to the power n minus 1. I have multiplied the powers with n minus 1. Then 2 into n minus 1, likewise n minus 1 into n minus 1. Clear? So this is the sequence. This is a general sequence of the Wn matrix, and from here the DFT, endpoint DFT results as xn equal to Wn into small x. Clear? Now see one problem. See. The question is, find DFT of the 4-point sequence. Xn equal to 0, 1, 2, 3. The same problem that I have done previously in my last lecture. Now you have to do this by matrix method. Now you have to do this by matrix method. Here, we'll get the same answer, obviously, but the way the matrix method shows, that you have to see. You see the solution. Wn to the power k plus n by 2 equal to minus of Wn to the power k. This is what? Remember the symmetry property of the Twiddle factor. This is nothing but the symmetry property of the Twiddle factor. Also, W4 to the power 0 is 1. W4 to the power 1 is minus j. W4 to the power 3 is j. W square, W4 to the power square is equal to minus 1. So here I have got these values basically. These values I have got basically to improve my matrix, because this one I have to do using matrix. So first I have to compute the Twiddle factor matrix. So W4, here it's the 4-point DFT, so Wn will be W4 equal to, since the first row and the first column stands for 1, so in all the first rows and the first column elements, matrix will be W4 to the power 0. Here, now, gradually it is increasing. In the second column, the first element, as usual, it is W4 to the power 0. Next point will be W4 to the power 1, 2, 3. You can see, it's very clear. In the third column, it will be 2, 4, 6. And the fourth column, it will be 3, 6, 9. Now, what will be the values? Now, what will be the values? You see, these values, first column and first row, all I have replaced by 1. Clear? First row, first column, all I have replaced by 1. Clear? Now, the others one, I have kept the second column as it is, W4 to the power 1, W4 to the power 2, W4 to the power 3. The third column, W4 to the power 2 is as it is, W4 to the power 4 is equal to W4 to the power 0. So I have replaced it. Again, W4 to the power 6 is W4 to the power 2. So I have replaced it. In the fourth column, W4 to the power 3 is as usual. W4 to the power 6 is W4 to the power 2, like this. And W4 to the power 9 is W4 to the power 1. So accordingly, I have replaced the values. Here, all of you, I have replaced these values. And then I have written the value of X4. X4 is obviously it's a 4.1, so 0, 1, 2, 3. It's a column matrix. Then get the sample value of DFT. X4 equal to W4 into X4. So we get this. The simple matrix multiplication. You will multiply W4, this one, into X4. You get this. The result will be a column matrix, obviously, because W4 is a 4 cross 4 matrix, and X4 is a what? What is X4? It's a 4 cross 1 matrix, isn't it? So 4 cross 4 into 4 cross 1. 4 cross 4 into 4 cross 1 will give you obviously 4 cross 1 matrix. Right? So this the value of DFT X4, capital X of X4, is a 4 cross 1 matrix. Yeah, that's all for today. And study properly. And in the next class, I'll be discussing the properties of discrete Fourier transform. Thank you. Have a good day.